Good morning, all. I'm not sure I would have accepted a keynote spot if I realized it was this early in the morning, but hopefully you guys survived okay last night. Anyone here ride the mechanical bull? All right, and you still made it back, so that's amazing. So good to see. Yeah, I love LASCON. It's definitely a different vibe than a lot of the conferences you go to that are much more corporate. It's amazing to see how packed it is this year as well. Like it's kind of like standing room only in the hallways sometimes, and that's great. I mean, this space is actually pretty big when you look at how many seats it has. So the fact it's sold out and everyone's doing hallway track the best way they possibly can is great. And in a lot of conferences, especially small community ones, it's really tough for the vendors to really get any love because they're all kind of off in the corner and no one's really over there. But man, you guys are doing a great job of interacting with the vendors, probably because the food's over there too. But it's amazing to see just how. So definitely support your vendors, hang out with them, talk to them because they're the ones who help pay for all this stuff. So thank you very much. And with that, I'll kind of get started. Um, does anyone remember an old sitcom from I think it's the Mitchell and Webb look? They had a goofy thing called Number Wang in the first couple series. This talks basically number wang. So we're gonna spit out random numbers and someone's gonna go number wang and that's basically it. But it's more about like, how do you think about numbers and number spaces and sequences as a hacker, as a developer, as a human being, and what do we do with them and how can you abuse them basically? So this presentation I want to dedicate to the folks at Bellingcat. These are folks who hold authorities accountable for human rights abuses worldwide at extreme personal risk to the people doing so through open source research. So you talk about folks who are really in the front lines of doing open source, open intel research. These are the folks who are really putting their necks on the line for it by literally doxing GRU assassins through their passports they stole from the data dump and finding sequential passport IDs to identify other spies. So these are folks who are not playing around and they put their neck on the line for all kinds of stuff. If you're not familiar with what belling cat means, there's a fable of all the mice getting together and say, you know what, this cat sucks. It keeps attacking us. It's terrorizing us. We all agree we're going to put a bell on this cat. Who's going to do it? So to get started, let's say you go to the DMV and you sit down or you walk in and there's a little ticket number machine, the dreaded ticket number machine. There's no sign saying what the current number is, but they probably call them out. You grab a number, says 74. I'm like, okay. What do you know about that? Well, you know you got 74. You know there's two digits. It's probably 1 to 100. The ticket's probably not big enough to put a three-digit number on it. You get a general sense of like the scope and size and scale of the number you're looking at. But you don't know when your number is going to come up. Like, are you going to be there all day? Are you going to be there for 5 minutes? How does it actually work? So all you can really do is try to get another number. How do you get another sample? Well, you just sit down on your butt and you open your phone and you wait a little bit. So the next number they call out is 82, and you go, oh crap. If I got 74 and then it's called that 82, does that mean we have to go all the way around again? Am I actually like almost 100 behind at this point? Am I going to be here for like the next 3 days? Well, let's play some Candy Crush, something like that. Wait a little longer, figure out what's going on. Let's see what the next number is. 85. Crap. Okay, yes, I'm stuck here for the rest of my life. I will not leave here anytime soon. But you know what? I'm already here. It's a pain in the ass park. Let's at least list for one more number. 67. Okay, that's great. There's actually a chance. There's a chance they're calling them out of order or they're allocating them based on what type of service or thing they're doing, right? This is a really common thing that happens all the time. You're involved with some sort of process. You get assigned an identifier of some sort, or you see it. It could be your receipt. It could be your social security number. It could be your driver's license number. And those numbers are allocated in a certain order, and they tell you a lot just by having one sample, and they tell you a lot once you get more and more observations. For folks who went to school, which does not include me apparently, the feedback I got was that there's a well-known problem called the German tank problem, where folks in World War II, the Ally estimation of World War II, or sorry, Panther tank production was estimated to be 1,400 per month, which is quite a lot of tanks. And there's a lot of concerns about there's this number of tanks. How are we going to be able to go up against that? Then the statisticians got involved, and what they did instead is they took parts that were blown off of destroyed tanks and started tracking those numbers. They started looking at based on the gears and the wheel numbers and the wheel molds and the engine parts. If we had enough of these together and we start counting them up, like what's the actual maximum production rate based on the observed serial numbers of these individual parts? And they came up with a number that was much closer to like 250, 260, and so on. When the Allies won the war, they actually seized the documents for production and they looked at it and it was almost spot on. So the statistical method of doing estimation, commonly known as the German tank problem, is pretty accurate with enough samples. And of course, the more samples you get, the more accurate your estimations are. So only 3 samples here for ticket number will give you a good sense for the mean, the max, the rate of change, things like that. And of course, there's it's a little more complicated than that. But these days, we pretty much put an identifier in everything. So your credit card's got a number, of course. You got documents. Every document's got an ID, 1 or 10 places. Your phone's got a million different identifiers, from its MAC addresses to IMEI to each individual part and chip to serial number. Your car's got a bajillion numbers all over it, from your VINs all the way down. I mean, your babies get a number. They get lots of numbers. If you ever, have a baby at the hospital, you get so many different unique numbers tied to your baby. You get like the date, the time, the operation, the person, the doctor, et cetera, right? So we just put numbers in absolutely everything we possibly can. Even things that are like more temporal, like this individual microsecond that we're speaking, technically has a number associated with it, and we're actually tracking in real time. So there's at least one log being created for every microsecond in this room, probably 30 or 40 times based on all of our devices. Just someone is logging somewhere this particular microsecond of this talk. Um, so these numbers are everywhere. Everyone likes to put numbers in everything because they help you discover things, help you keep track of stuff, but they also leak information all over the place. So this talk is really about how do you identify those information leaks, how do you abuse them, how do you do like useful security things with that data, and how do you think about and rationalize security considerations and limits based on numbers and sequences. So most identifiers are short. People don't like entering long numbers into your telephone. I mean, we have so many. Like, I absolutely hate using the telephone. I'm like millennial who I will do anything but call somebody. I'll actually text my wife and ask her to call someone for me because I just can't do it. I'm like, I don't want to speak to a human being. She is so much better at the people side than I am. Like for me, it's a step too far to go on the phone and talk to somebody. I had a dear friend who liked to call me all the time, and I finally had to let him know, like, every time you call me, it hurts. Please stop. Like, we have the internet for a reason, buddy. Like this is why we do it this way. Um, but phone numbers are fairly short because you have to at least be able to memorize them. At least before we had cell phones and no one knew what our contacts were anymore. You had to know your number. If you're of the age of 25 to above, you probably had to memorize your parents' phone number at some point. These days, I don't think kids even know how to even look up a phone number. They just click on their person's name and that's it, right? It's a little bit different. But as a result, these numbers being short means they have to be really dense. You have to put a ton of information to every single identifier, otherwise it's going to be too long. So as a result, these number spaces are really tiny and they're really kind of full of information. And even a small change to that number would actually point to another valid record. So when you talk about like this from a security perspective, the really obvious use case here is like insecure direct object references, right? You go to the doctor, they give you your test lab results. You go to the URL, you see it says 1115. You go, hey, I wonder what 1114 was, and like, oh, this person's got gonorrhea, and now I just committed a felony by accident. So that's kind of how, well, one, how easy it is to commit a felony these days, but two, how terrible our information security architecture is that we still have those types of vulnerabilities all over the place with small sequential identifiers. Um, so we encode information everywhere. Part of that is because if you're a developer, like let me go back a little bit here, but let's say you're a developer, you're building a new web application, and you say, I want to add a Boolean field to this table. I want to say, did this thing happen? Is the user paused? Have they logged in yet? Have they done something else? The first thing your more senior comrades are going to say is, you never want to use a Boolean. There's no point in ever using a Boolean record in a database table ever because you spend the same number of bits and you only get one bit out of it. You're going to basically use a full D word or 32-bit value to store it, but you're only really going to get one bit. So what do you do instead? You stick a timestamp in it. You stick something else. You put some other, like you put a bit set or a field or something like that, because you don't want to like just waste database table space for no good reason, especially with bajillions of records. So instead of using a Boolean of like, have I logged in or not, you'd use login at instead, and then use that timestamp on the login at to show when it was. But now you've also gone the other way around. You've now said, instead of storing a single bit, you now actually encode the time of the last login, which may not be something you want to expose to the user, but maybe expose the user through JSON output, REST APIs, et cetera. So stepping back a little bit, another fun one is social security numbers. So social security numbers are really, really tiny space. It's like 9 digits. There's no letters or anything like that. The first 3 digits are the area number, generally related to like the state or wherever it's issued. Next 2 are called your group number, and the last 4 are the serial number. So we all have 4-digit serial numbers if you have a social security card. That's not a lot of space. Like you get conflicts pretty quickly. So what SSA does is they actually issue kind of monthly or annual guidance, depending on the year, about what numbers are valid for issuance in a given year. So they say in a given year, this area number plus this group number, the group number will never be higher than X. So if you, as an employer, need to validate a social security number, you can always guarantee by going to the website, okay, is the group number larger than 85? Well, this number is invalid for this particular time period. But of course, these numbers being so small, there's tons of conflicts, right? After a certain number of years, they start to rotate, they start getting mismatched. Like you have to know the birth date to also tie together with social security number to make it all work. So social security numbers are really interesting, I think, just because like we're all stuck having them. They're really low entropy, and it's really easy to discover someone's. I have me and my siblings were all born in Hawaii, so we all have the same prefix. We're all in the same kind of time period. So just knowing the first 3 digits of someone's security number, you generally have a good idea of where they were born. And it's just a huge information leak all the way through. And this is just one of the really tiny identifiers we deal with all day long. Another one I really like to point to, this is probably one of my favorite graphs in the world, and not by me, of course, but like someone at Data Genetics built this. They did analysis of leaked PIN numbers from a bunch of password leaks and then graphed them. But generally, the idea is like if you let the users pick an identifier, they're going to do a worse job than anything else you could possibly do. Users do not want to be just like passwords. Everyone hates passwords, but if you have to pick an identifier, if you have to pick a username, you're going to be even worse than picking a password. Like no one picks a random username. They pick their username that's like, you know, Call of Duty Pro 2009 or whatnot, and they use that for the rest of their life. Um, I have a child who is now 15 who has an email address with the word Snooglebean in it, and they still use it, and they're so embarrassed by it, and they can't figure out how to change it, and they will not let me help them set up forwarding. So you kind of get stuck with these usernames the rest of your life sometimes, and yeah. So user chosen IDs are really bad. PIN numbers are really the worst because they're so short. One of the neat things from this graph is that they said that statistically 1/3 of all possible 4-digit pins can be guessed by just trying 61 attempts. That's it. That's how common. This is how predictable human beings are. And this graph's interesting because the bottom left side are all your 00, 19, anything starting with a 1 and a 2 and a 9 and so on like that. So that's your like 1900 years, things like that. The big diagonal line going from the bottom to the top right, those are all the sequential numbers. So 1 1 1 1 1 2 2 2 2 2 3 3 3 all the way up like that. And then you've got these big streaks kind of up and down there that are definitely like different sequences, different patterns. And you get a few little dark dots there. They're like the pin number that no one's ever going to choose. So pick that pin number apparently. It's kind of neat that there's actually just a couple spots like literally nobody chose as pin out of 10,000 numbers. So a little bit of a dig into this chart here. You can see like 999X in the bottom right. You can see 7042 is kind of up there, that little bright dot. You've got like, the 8775309, like the song lyric is one of the bright dots there as well. When you start plotting out identifiers onto a graph, some patterns start to pop out, and you really start to understand the system, the people, how people are doing it. Some of the numbers here are based on like telephone keypad, like you just go straight down the line or diagonal on the keypad line, so those pop up as well. But I love these things because you see things that just aren't really obvious when you start plotting it out like this. So every identifier, even if it doesn't look like a number, is also a number. So let's say you've got an identifier that's a license plate, like ABC1234 or whatever, right? That's still technically a number. You can either decode those letters to a numerical value, just give it hexadecimal, give it like a base 26, base 38, and then turn it to a decimal value, or you use it as a lookup index to an existing table. So you go to the DMV and say, for this number, what is the index of this particular unique string? And it'll tell you what it is. But one of the identifiers that I love, just because there's so many ways you can leak this out on the network, are Dell service tags. So Dell service tag is like the little alphanumeric code in the back of your laptop or server that says how you look up your warranty information. Like, are you still in warranty or not? But the neat thing about Dell service tags is one, they're visible on every machine. So you can go on eBay and find the Dell service tag, just print it on the label in the back of the photo, and just find them all over the place. You can actually pull them out of the iDRAC web UIs. So the iDRAC TLS serial number, TLS certificates will actually tell you the service tag in a lot of cases, as well as some of the other config endpoints. So even if you don't have authenticated access to a DRAC server, an out-of-band BMC device, basically, you can get its service tag and then find all the specs of the server. When was it purchased? How much memory does it have? When was it shipped? All that other fun stuff. But Dell service tags are these alphanumeric characters, but it's actually just really a base 64 encoded decimal number, which leads you to something that Dell calls the Express ID. An Express ID and a Dell service tag are the exact same thing. It's just one's encoded as base 36, one's encoded as decimal, and there's a little bit of like bit fropping here and there to get there. But if you take that Express ID, then actually treat that like a decimal value, well, now we've got the value 38,000,006,012, etc. So if you start gathering just random service tags, let's say off the whole internet by scanning all the iDRACs and start plotting them out on a graph, you end up seeing like pretty neat patterns. Like here's a batch of servers that are produced at once. You want to say, okay, how many excuse me, PowerEdge 2600s were built in this particular period? Well, we can use some sampling. You can get a good sense for the density. So let's say you're in charge of security for your internal network. You can gather all your service tags, not get just like, are these things under warranty, but how old are they, when they're manufactured. Lots of really good information about your assets that otherwise would be tricky to pull out through any other method without, let's say credentials. So identifiers often include categories, sequence numbers, and checksums. Mostly, checksums would be an example of like your credit card LUN code, right? Like back in the day of AOL, when they gave you all those little CDs in the mail, the coasters, it was too expensive for them to actually try to charge your credit card. So you can give them any credit card that passed the LUN check, and they give you a trial for 2 weeks. And I had internet for like years that way. You just like every 2 weeks you give them a fake credit card number and off you go, right? Because they're not going to try to bill it until you actually get to the end of your trial period. And so it didn't really matter. Yeah, it was a fake credit card number, but they weren't actually trying to bill it. So it wasn't until it became much cheaper for businesses to do the pre-auths that kind of went away. So until then, you're kind of stuck using that checksum code as the only real security validation for that particular card number. But a lot of numbers will have a category ID. They'll have sequence numbers built into them. One example I really like to look at because it's everywhere are vehicle identification numbers. As of what, like 10 years ago, VINs need to be externally visible on all new models of cars. So you can walk up to the front of almost any car, look right over there by the driver's side window, and just visible right there is the VIN number. And it's legally required now to have your VIN number exposed on your vehicle. So what does a VIN number actually tell you? Tons. I don't know if you've ever gone to like a VIN check, like buying a used car or something like that. You'll see like the VIN facts, the car facts. Those are more of like lookup table. They'll show you the history of that ID. But using just the ID alone, you get a lot of really interesting, detailed information about the car, the manufacturer, where it was built, which country it was on, the type of characteristics of it, like engine size, brand, and type. It's got a single security code. This like check digit here, the X is actually being used, some sort of secret on the manufacturer side. But again, it's only 1 byte, so it's only can only be so good. Um, Another interesting part here is the. Oh, I'm sorry. The slides did not. There it goes. They're off a little bit inside. That's strange. All right, are we synced? Yes, we're synced this time. Great. Um, so the interesting part here is there's only 6 digits for the serial number of the car for that particular plant, model, factory, et cetera. So this tells you a really interesting real world limit. You're never going to have more than 1 million cars manufactured at the same plant with the same model information. Otherwise, it just doesn't fit. You literally can't issue a VIN for anything that big. So numbers are cool because they describe the physical limitations of the world that they're a part of, right? So you don't want a really long VIN number because then you can't type it in and it annoys everybody. But if you get a too short one, you end up with problems like this, where now you can never make more than 1 million cars for a given factory in a given year and model. So identifiers really are super information rich. They often tell us the location, like when something was created or where it was created. They tell us the time of creation, like how old it is, when it was created. And then if you have more than one identifier and you can look at them, you can start figuring out the rate of change. How quickly are identifiers being allocated? So there's a couple of fun examples I want to talk about, but we mentioned before, these really represent often the real world limitations. You typically create an identifying system to describe some physical thing that already exists. And so if you have an identifier system that is, fairly short, you know that there's only going to be so many number of those events happening in a given period of time. Otherwise, you would have a bigger system. So I love the fact that like a single digit or a single number can tell you a whole lot about the whole system that created that number and how it's being used. So we'll go into a couple examples here that I love. But the general idea is with a small sample set of any given identifier, we can really learn a lot about the system and start reasoning about the security properties. So, why does it matter? Of course, ACLs are not just for the web. Insecure direct object references are everywhere, including like telephone IVRs, a million different ways, right? Your Chipotle order number when you walk up and say, my number is 305, I'd like this burrito, please, or you take it from the to-go box. A friend of mine was joking during the pandemic that he was really happy that all these restaurants started giving away free food. You just show up and go to little, boxes and you grab whatever number you like and you leave. But yeah, so ID discovery allows you to, do data leaks and then really plan for different abuses. So one example that was somewhat recently, a friend of mine helped me report this, so I didn't go to jail. But if you go to Walgreens, for example, and you get a prescription, there's 2 numbers on your prescription. There's the first number, which is the 1, 2, 3, 4, 5, 6, 7 here, dash, and then another 5-digit number. Now this looks very sequential, right? This is not particularly interesting. But if you start looking at, like, let's say you happen to have a prescription bottle at home, you look at it, you'll notice the last 5 digits are all the same based on what store you go to. So every physical retail location has a different 5-digit number there, and it's static. So the one in South Lamar, for example, is 01933. That's going to be the number. The number before that is a really small sequential digit. Every time you get a new prescription from Walgreens, they +1 it and they ship another one. So if you get booked 2 prescriptions back to back, your prescription numbers will be really close together. So you can tell just by, let's say you fill the prescription once a week, you know how many prescriptions that particular location has filled between that week just by looking at the differences of your own prescription, basically. Even worse, unfortunately, the IVR system and even the website at one point would tell you information about the prescription using just the prescription ID. And this is like, what, a 7-digit number that increments that you know what the ranges are. So if you go on, at this point, this is like 6 months ago before it was fixed, you go on the Walgreens website, do guest express refill, you type in the number, it would say, great, your prescription is ready. Thank you. It's ready for pickup, ready to be put. But it wouldn't show you the name on the website. However, if you go through the IVR system, or if you go through and look at your browser web tools or burp or whatever, in the JSON response coming back, it actually told you the full name of the person. So even with no login whatsoever, just a sequential number that you can guess based on any other sample out there. You can go through and get a list of all the different prescriptions the particular pharmacy's been filling, and until recently, the name of the people getting those prescriptions. So you knew who's got gonorrhea, you know how often they treat it, and of course, this stuff becomes very quickly a felony, right? Because you're accessing PHI, and everyone freaks out. Prior to this, the first time I reported like an IDOR vulnerability in like uh, a medical provider's test portal, like document portal, they immediately sick their lawyers on me and say, "What did you do? Who else do you look at? We're gonna send the cops to you." I'm like, "Dude, just fix your stuff. I don't want anyone else looking at my data. Like, just fix your thing." And it took like 3 weeks to get them off my butt and actually say, like, "I'm gonna sick my lawyers on you if you don't fix this stuff." They're like, "Okay, fine." And I was, it was ridiculous. Like, just fix your stupid sequential IDOR bug, right? It was not a big thing. So the prescription one here, this is like real world. This is recent. Like people just screw this stuff up continuously. And I just love the fact that you can, how busy a pharmacy is, not just by how long it takes for them to fill your stuff, but also by looking at your own prescription bottle and saying, okay, this is how much business they're doing. Similar perspective, Chipotle. Uh, actually going back to this one real quick, have you ever noticed that Walgreens no longer has a trash can by the front door? So this is a big change about 2 years ago. Um, Prior to 2 years ago, when you got a prescription, they would say, printed on the prescription, it would say, "Do not throw this away." And people, of course, would say, "No, I will throw this away. F you, I'm gonna throw it in your trash can." And so they'd walk out, they put the prescription thing directly in the trash can, and then someone would walk over there and grab the trash out of the trash can and walk off with it, and basically get a list of everyone's prescriptions in the last day or so. So folks were literally just stealing the trash bags from the front of the Walgreens to get all the PHI of the folks who were filling prescriptions, and using that to come back and say, "Oh, I need to get this thing refilled," or "Sorry, like I lost my codeine, I need more," or whatever, right? That. So it's being used for prescription fraud. It was just funny that it got so bad that Walgreens literally got rid of the trash cans in the front of the store and moved around the side. So if you're looking for the trash can at a Walgreens, you have to go around the corner now because people were doing too much fraud with the prescriptions from the trash bags. Um, so going a step further, like Chipotle, which is, I don't know, this is more of a fun one. Most retail stores, POS, they have like an order number. The order number generally resets each day they open up for business. And you can do the same thing. Like how many burritos were sold during this given time period. So you can show up and dig through the trash can like a raccoon, pull out a couple of receipts first thing in the morning, then come back at lunch, look at the couple of receipts, like, oh, you sold 45 bowls of X, and so on. But you get tons of other identifiers. You get the store number here, you get the order number, you get the time of date, you get a lot of really precise information in a receipt. And this is literally like a web log timestamp. Um, Sequence number, time and date, location, all kinds of fun stuff. You only need about 4 or 5 receipts over a couple days to have a really good graph of how busy the Chipotle location is. So it's pretty minor. No one's really going to care if you steal their Chipotle burrito, hopefully too much. But it is interesting just how pervasive this stuff is. Another one I really like is when you go to the, well, like is probably the wrong word. You go to the doctor's office and they give you a printout for your here's your follow-up visit, or you take this to your lab, whatever. Almost unfailingly, they use a browser to print out a web page. And what do browsers like to do when you print a web page? Put the URL of the web page on the bottom of the page. So you say, "Oh, great, here's a URL. Let me go type that in and change the number real quick." And you see the previous person's lab stuff. And it's still ridiculously everywhere. Like they don't expect anyone to find the URL because it's not publicly visible to the user, but because they put it on the page, it's pretty easy to go find it again. And even worse when you see like the Internet Explorer telltales and stuff like that. Oh my God, you guys are still using IE. Please don't. My dentist tried to make me use this like IE-based kiosk once. I'm like, I'm going to install Linux on this before I use your browser. So like, I'm either going to like write it by hand and then you're going to scan it and put it on the same crappy machine, or I'll reinstall your machine for you. And I just did the paperwork, and he probably uploaded it right back to the portal. So beyond, we talked about Chipotle being like business intelligence. So like, really minor leaks can actually tell you useful things about an entity or a company or a business. Like every other nerd in the world, I decided, you know what, I'm smart. I can beat the stock market. And I'm going to do that through information that's public that no one else is looking at. I'm going to find my own alpha, right? So if you've done this too, don't worry. It's part of your normal life. There's a sequence in your life in which you think you're smarter than everybody else, and that you are somehow going to make some money by being a nerd where other people have not done this. It doesn't work, but enjoy it. Just don't lose too much in the meantime. Um, I'm not going to be smart enough to beat a prop trading firm. But one thing I noticed just over the course of a bunch of pen tests is that there's a common e-commerce platform called Oracle Commerce ETG. Each time you register for a new user account, it gives you this dying user ID cookie, which is sort of sequential. It has like a really long, like a billion number kind of prefix, like a number in the billions. Then it has like a suffix in the end, and the very front of the number will bounce around. So it'll be like 802 billion, something, the 809 billion. But the middle digits were pretty much sequential. It was just kind of the front prefix and the suffix that were changing a little bit. It took me a little bit of digging into it, but realized like the suffix was actually based on the load balancer. So like 802 billion to go to device A, 902 billion go to device B, and so on. So if you take that into account, and you scrub those guys out, and you start looking at the numbers that are change incrementally. Let's say you decided to just create a web account at a couple large public traded companies repeatedly for a few months, and saw how the numbers worked out. You could theoretically graph out their business and how well they're doing, especially leading up to their earnings reports. So, for example, this is a log. The numbers here are log because the order sizes are very different depending on stuff. So, in this case, Couch Shop, which you can imagine is a large online retailer that was well known for taking Bitcoin. Flower Shop, which is probably the most generic flower shop you can find in the world. Um, and of course, a jewelry shop that's pretty much well known, does a lot of e-commerce stuff as well. So, graphing all these kind of side by side over the course of 2 months, you can see how does their business ebb and flow. They all have kind of spikes or dips on the Mondays and spikes back up on like Tuesday. They all have pretty good business over the weekends. And there's this big kind of spike with Couch Shop here, and this is actually because this is when they decided to start taking Bitcoin as payment. So you can see like a big spike of like all the Bitcoin people blowing their money on couches. Um, but it was neat. So I actually had a bit more data on this. Like, I don't, for some reason, people bought a lot of jewelry on April 13th, 2015, compared to every other day. I don't know what day it was. There was a Mother's Day period that I monitored as well, but I couldn't find the data set for it. But the Mother's Day period is really funny because you see this big spike in flowers, big spike on jewelry, and a drop in couches. So what was interesting about this is like I went through the whole process of like, okay, I didn't actually make any trades based on it, but I went and gathered the data. Said, okay, based on this, I kind of know what your new register, if every new user you sign up is worth this much money to you, and you sign up this many new users, therefore you made or didn't make your numbers, right? There's a lot of other variables like how much do they spend? Is it a spam account? Is it someone else doing what I'm doing, creating fake users? Like, so it wasn't actually useful from trading, but it was really interesting from a graphing perspective. So it's also kind of fun to look at this stuff, and this platform works the same way today. This is 2015. It's now 2024. It still gives you sequential user IDs when you register. The only difference now is there's a CAPTCHA. So you can't just do it automatically with Ruby script. You have to go click a couple of buttons every couple of days. But you don't need that many samples, right? You can still create an account once a month and still get a pretty good sense of the rate of change for any one of these publicly traded firms. So just really tiny samples are still enough to really do useful stuff. So just checking on time. So it's really important to understand how identifiers are allocated and how they're incremented and are they predictable and so on, because it really defines how you defend your applications. If you're using like UID v4s through your entire app, well, your users probably hate you, but it's probably better for security, right? But sometimes it's not really clear whether an identifier is random or not. Here's an example. Anyone offhand have an idea of what this number means? It's not like alphanumeric or anything like that. It's just like, if you've stared at enough web apps lately, you might notice the first part of this number is probably contains some information. Yeah, it's hexadecimal, and it's a JavaScript generated timestamp. So the first 32 bits are actually Unix timestamp, which refers to 2024, 1021. So October 21st at 7:30, when I should have been working my slides, I did this. So that's an example of like how you can just take a number that doesn't really mean a whole lot, realize part of it's really a timestamp. When you start looking for timestamps like the 172, 167s, all that kind of stuff, you start to just start memorizing. You see these numbers everywhere, like every web cookie, every request, every session. You start seeing like timestamps in your dreams. Like you start to just like, I spend way too much time thinking about numbers. And I swear, like Unix timestamps are like the undercurrent of the entire internet because you see them just attached to so many different things. Another example here, this is looks like a UID. Normally the UID version field would be where that number 8 is. This is probably not a version 8 UID for a bunch of other reasons, considering that they're only recently developed. So they're not really clear what this thing is. It's probably UID, but it's not really a known UID. Let's dig into a little bit more. Oh, it's actually a SQL Server encoded UID v4. So SQL Server, for some insane reason, decides to frob the bytes. So it'll take whatever your UID is, like v1, v2, v4, or whatever, and then it reorders the bytes, the very prefix on it, when you generate the UID on SQL Server as an index. So you'll get a value that could be a leaky UID v1, for example, but you won't know it until you do the SQL Server specific byte frobbing at the beginning of it. So you have to kind of dig in a little bit more. You say, okay, well, this doesn't look like something I know. What if I go through these other kind of encoding mechanisms to figure out what it is? Another example, this one is another UID, but you can see here that it's got a UID v1 prefix, so that the second set of digits starts with the number 1, and then there's some variant fields we'll go into a little bit later. But this is really interesting. So this is actually a number that was pulled out of Microsoft's operating system. It was, until we're going to go more to this a little bit later in the section, but effectively, early UIDs embedded the MAC address and the timestamp in every UID generated. Microsoft, of course, then used the UID generator to create a lot of components in Windows. As a result, there's a lot of parts of Windows that hard coded the developer's MAC address into them, which we now corresponds to this particular Dell desktop at this particular date and time. So we can go find this developer's desktop, basically, if you really want to start digging for it and looking for it. It's kind of a neat way of encoding information. We'll go into more about this type of leak a little bit later. But the kind of the summary here is like it's really hard to tell just by looking at a number what's encoded until you start doing all these little like bits of transforms on it. So how do you go about discovering numbers? You generally need to have some sort of sample identifier, something to kind of seed it. You need an action that takes an ID and tries to resolve it into some sort of attribute, like you know, ping response, ID exists, doesn't exist, ID access denied, or that tells you something about it, like an Oracle lookup. You can say, this ID, this IP address associated with this country, this ISP. You got to record it somewhere, and they have to be able to correlate the attributes across all these different things to get there. So I love telephones. Like my entry to security back in the 90s was war dialing and dialing into random stuff and generally causing havoc, like turning Kmart's HVACs on and off and messing with transmission towers for FM and generally annoying all of the IBM folks who operated a modem bank downtown. Um, and let's say the most basic way you can explore a telephone network is to buy a notepad, get a phone number, and just start typing in buttons. And then depending on what rings out, you say, okay, a human answered, I got a modem, I got a whatever, write a little note on your grid or your notepad and move on. And that's pretty much it. And then you say, okay, where are all the modems? Let me draw a link between all of them. And that's basically it. That's a super easy way to do telephone network mapping. But then, of course, you get a modem. And once you have a modem, things are way more fun. You can start using things like tone loc to start doing automatic dialing, voice detection, et cetera. But it's still pretty slow because you're looking at even like a prefix like 555, 454. There's 10,000 numbers in a block. It'll take about 30 seconds to call each number, and you can let it go even longer if you don't set a timeout on it. So as you're just kind of slowly cycling through from 0000 all the way down to like 9999 in the bottom, you start to see some things pop out. You start to see like, okay, here's a voice, here's a modem, here's a call, here's a thing. But this is super slow, so we can ramp it up a little bit. It takes about 83 hours to dial every line in a prefix, and it gets more patterns. But of course, the faster you can sample, the quicker you're able to get good data. So let's speed it up a little bit more. So you can start to see the patterns really start popping out. Sorry, it's a little washed out on the screen, but the idea is the little green map at the top. Those are all modem banks from IBM back in 1997. The red line, which now kind of washed out here, that's actually a bunch of lines that return a telco error. They go D D D. Your number's not right. And then the blank lines here are the ones where they just ring out. No one ever picks up because the phone company hasn't actually allocated them, but they just ring forever basically. So because this is phone numbers are basically a power of 10. You usually have these blocks of 10,000 numbers. We map this graph starting at a power of 10 decimal, 0 to 100. So every line's 100 numbers, then it's basically 10,000 across the board. And because we're mapping the graph to the same way they're being allocated, these patterns show up nice and pretty, right? You get these nice clean lines showing how things are being allocated. So we can take that same approach and let's apply that to IP addresses. Now, IP addresses a little bit differently because they're not done as powers of 10, right? They're done as powers of 2 for CIDRs and subnets, things like that. So you do the same approach. I need a starting phone number. I'll take an IP address. You can scan it. You can identify it, like what fingerprints is running. Is it a printer? Is it a whatever? You can create a big markdown file of all your results, and then you can maybe color in the boxes based on what type of thing you found. So you have here's again similar kind of block diagram. This time it's 256 numbers. You got your dot .0 at the top left, your .255 in the bottom right, and we're gonna do kind of a quick ping sweep. Okay, great. So we see there's something at .1 that responds, that little first green thing. Then we've got a block of numbers at 10 to 15, another block at 20 to 25. In the middle range, right around 128 or so, is a bunch of stuff. It's usually probably like a DHB range because that's usually a good starting point for DHB prefixes. And then at the bottom, you've got some of the stuff kind of hidden down like 240, 241. But until we actually get a little more detail and start doing fingerprinting these devices, we don't really know what they are. So let's say we now do mmap with fingerprinting and we start classifying based on what they are. Well, now we can see like, oh, okay, the .1 is actually our router. The green ones are actually network switches. They're actually kind of controlling access to the different subnets. The top red ones here are servers. The yellow ones are printers. And the .128 is also a switch. Down at the bottom there, we got 240. We've also got a switch and then some IP cameras. In the middle are all of our endpoints. Those are all like Windows desktops, things like that. So we've got a pretty good idea of like how this network's been allocated. We know that they put all their servers at a low end range. They've got basically one switch per kind of group of devices. All the printers are kind of clustered together. And then someone screwed up and put the printer in the DHB range by accident, and that's why the big yellow dot is there in the middle. That shouldn't be there, right? That's something that obviously was a mistake by somebody. And then at the bottom, you see like you've got probably a dedicated switch for your IP cameras because they probably have a lot of bandwidth you need to bring back images. So we start to really understand like how the network is laid out pretty quickly just by doing a couple iterations of this kind of discovery. And of course, you don't have to do all the IPs, right? You can just sample that. You can just kind of pick like every 10th IP and just kind of go through it. As long as you're covering kind of the network boundaries of your .1s and .255s, and you kind of sample the rest of the space, you can start getting a picture really quickly without doing a full discovery. So if you take this approach and then apply it to like a /16 in a large corporate environment, this is typically what a /16 looks like when you zoom out. So you'll notice right away, this is, I'm sorry, it's a bit of an eye chart, but the left side of this is a bunch of little blue dots. Those are all your routers. So those are routers who have the .1 address, .123. Cisco typically have the first few octets of each /24 allocated to the routers. Then you see kind of a sea of like, blue, a sea of purple, a sea of these other ones down here. That's kind of a mix of your servers, your endpoints, your network devices, your NAS storages. But it's pretty clear that admins typically like to group their stuff together. And you can figure out how they're being grouped, where the dead space is, uh, you know, where things look that are kind of weird. Like we've got these big stripes of bright red here that kind of stick out. Well, ends up these are BMCs. This is the management interfaces of all the servers that are on their own separate management network in this particular IP range. But it isn't until really you zoom out a little bit that you really understand how things are being allocated. Now, if we do the same thing for like IPv4 public space, you start seeing some patterns pop out. So this is just I think, a Belarusian broadband network. But one thing you'll notice right away is the same thing happens. The left side of the graph, you see all your routers and switches. And then you see all your broadband IPs are pretty densely packed here on the rest of the IP space. And depending on which one of these little versions of the graph you look at, you can start to see a diagonal line going across it. And one thing that's weird is like, why is there a diagonal line? Like these are systems that should all be, got your DHCP server, got your IPs, got your broadband. For some reason, this ISP staggers out their DHCP ranges based on which subnet you're in. So if you're in, the 10.20.30, 10.20.40, each time you go down a notch, they actually shift over your beginning DHCP address by a couple, and that creates these nice diagonal grid lines, but you don't notice them until you really zoom out far enough. So a lot of times, all it takes is getting enough samples and then getting enough distance from those samples to understand what the allocation of the space looks like. So if we looked at this as a single subnet, it would look pretty boring. It was like there's really not a lot of signal there. But as you start going out, you start seeing those patterns pop out really quickly. So this is kind of the obligatory internet map. So I say obligatory was anytime it ever shows you a geographic map, they're showing you a population graph, always. There's almost no difference. Unfortunately, the only exception there is Africa. So almost every other continent, you're going to see the density of IP space mapped directly to population centers, where Africa, unfortunately, the center doesn't have a lot of connectivity. So these graphs are interesting because they show you like, okay, we do have a lot of IP space. It's linked up. This is a combination of some 2015 data from Shodan and from Project Sonar that I worked on. We start looking at it from a Hilbert graph, though. Hilbert graphs are where you start mapping IP space where each network block is mapped out as closely to its neighbors as possible. So you kind of make little spiral, curly cues basically of each of the blocks that you can kind of group them together. But this is the left side of this graph is the full IP space. We did a little zoom in here in the top quadrant. You'll notice that some spots are really dark, some are really dense. And the one we're zooming in here is these little red dots. And the further we go to little red dots, we start to figure out that there's some subnets here where just everything's red. Well, what the hell is going on? Ends up, this is a German ISP where every home user is given a Fritzbox router. And the Fritzbox router has a SIP endpoint running on it because they actually do VoIP over IP as like their actual home phone service. But their endpoints, their routers themselves actually expose SIP to the internet. So almost every single user in these particular ISPs has a SIP endpoint exposed to the internet, which is great for DDoS, things like that. So they've mostly, I think, fixed that since later put auth on it, but it's kind of neat to see how it breaks out. But again, the patterns pop up really quickly. You can see like, where does it make sense to dig into the network? Where is there density? Where are there gaps? But the short version with IPv4 is discovery is now it's so full, you can't really not find things. So there's about 3.7 billion routable IPs in the 4.3 billion possible with a 32-bit number. Of those, 774 million are already in Shodan. Like literally 21% of every possible IPv4 address has already been scanned and Shodan and it's already there. And if you pick any number out of a hat, like any IPv4 number that's not in the reserved ranges, like their 224/4 or your 10x and 192.168 and stuff like that, there's a 17% chance of that being a live address. So let's say you're gambling with your friends or playing D&D and you don't have any dice to roll. You can just ask everyone to give you an octet and then type ping. And that's basically a 1 in 5 chance of that being responsive. Do that enough times and you have your random number generator. So if you want to make a really lazy dice game, you can use the internet to ping random IPs and figure that out. But of course, you can weight the dice by knowing which subnets are denser and things like that, but it's still kind of fun. So IPv4 is so full at this point that it's basically just one big aquarium that everyone's scanning and sniffing and doing terrible things to all the time. And I love the fact that IPv4 started off being this thing that was so, like nebulous and hard to discover. Then folks originally were like, wow, no one will ever find my address. I'll stick it online. As long as there's no DNS, no one will ever find it. Now, every single live IP address is being tracked daily by the second by like 30 different firms. It's crazy how dense it is. So we all work in a big fishbowl. Now, going the opposite direction, someone did a Hilbert graph, Vasturiano, I forget his first name, unfortunately, but he basically mapped out IPv6 as a Hilbert graph, and it's a very different story. So in IPv6, every endpoint gets the internet times the internet number of IPs just for its own device. So you're looking at basically 64 bits assigned to every host, which is the crazy number. And the host is only using one of those IPs. So you got to scan the internet times the internet for each host just to find the host's responsive IP. So your range-based discovery is not going to work very well. This Hilbert graph is neat because it kind of shows you the kind of zoom in here. So in the center box here, these are actually the only really allocated ranges. The stuff up here, these are mostly like broadcast, reserve, things like that. But this box here is actually the entire like weighted space that's actually allocated to people doing V6 stuff. Now, if you go into this block, it's also a bunch of like allocations that are pretty much empty. If you want to find the real ones, you go into these little tiny dot boxes here and blow those out. And these are actually the ranges people are actually using. So it's like one thing I like to show is like the old Hubble graphs where they show you like zooming into like something like that. Like that's your IPv6 address, and here's the IPv6. Good luck finding it, right? It's just that level of scale. Like you're talking about like every mode of dust in the universe has an IPv6 address, and it's really difficult to find something like that. So what do? How do you discover IPv6 when it's that sparse of an environment? Well, the good news is on the local network here, you can find all your IPv6 friends right now. Just pop up your laptop, type ping6 FFO2 : :1 %, whatever your interface name is, like Ian0, and you'll get a response from all your other friends' phones, laptops, everything like that. Everything's V6 by default, and link local is everywhere, and you can do all kinds of cool stuff. One thing we do at work is if you scan a V4 subnet with our product, we also scan the V6 link local by default and just don't even bother asking you. And what we do is like we'll identify the link local address for a V4 address, map them together, find all the ports open on V4, find all the ports open on V6, and show you the difference on it and say, hey, there's actually a port open in V6, not open in V4. And it's pretty common for folks to screw up the firewall rules, especially on like network appliances, where a V4 will be completely locked down with maybe SSH open, but then there'll be like a Redis server open with no authentication on V6. So it's always fun. So if you haven't played with link local scanning, it's the best thing ever. So outside of link local, which is trivial, as long as you're on the same layer 2 subnet, you can find pretty much every V6 address instantly. And we're just using ping6 here, which is ICMP. Oh, sorry, the slides are shifting off a bit. So we're just using ICMP. A lot of devices will ignore ICMP and V6. So you can do a multi-protocol probe. Like if you use THP IPv6, the THC V6 tools, it'll do a multi-protocol. So it'll send like a SYN request, it'll send a UDP packet, it'll do a bunch of other stuff. You're just trying to get an error response from one of the endpoints saying, yes, I'm here, go away. You also notice that these IPv6 addresses aren't particularly random. Like you'll see a bunch of IPv6 addresses with FFFE in the middle of them. What that means is the things on both sides of it are actually the MAC address. So you've got 3 bytes on one side, FFFE, the other 3 bytes of the MAC address. So if all you had from somebody was their link local V6 address, you also now know their MAC address, which means you also know, the vendor and all other fun stuff, right? So if you want to go find public IPv6 addresses, though, it's an entire other thing. It's like an art. So I'm going to go a little bit faster because I'm nearer than a time. But there's a project called IPv6 Hit List, which does an amazing job of predicting in-use V6 values and ranges. So they basically sample the internet, try to find out which ones are in use, and then continually train their model on that, trying to find more and more stuff. And they're up to about 2.5 billion addresses that are in their discovery scope that they know are used based on a certain pattern. So really cool. They're up to about 30 million-ish, or depending on the 20 million, I think, in the most recent sample of IPv6 addresses that actively respond, they can discover using this algorithm that they built. And it's all open source. You can go download and stuff like that. So 20 million sounds like a good number of V6 numbers to discover. However, Shodan found 211 million. So why did John Matherly, who's a local here, find 211 million IP addresses in V6 when everyone else finds 20 million? Well, John did something really clever, which was infiltrate the global NTP pool. So Shodan has been registering their own NTP time servers for years. And they have so many time servers that, like, if you have any kind of IPv6 enabled machine, it's eventually going to hit one of their IPv6 enabled time servers, see you, and then immediately scan you. So there is some grumbling on the internet about it, and folks are saying, well, this is evil, you're kind of honeypotting it, this is bad. And I think the response is like, well, we're giving you time, aren't we? So Shodan does the best job that I know of identifying public IPv6 because of the NTP trick. So we're a little short on time, so I'm going to scroll through a little bit. I'll put the slides on later, of course. But so UIDs are actually very similar to V6 in that there's 128 bits. They're kind of random, but they're often coded. There's a bunch of different kinds of UIDs. The only kind you ever want to see in your own application is V4. And we'll get into reasons why, but effectively everything else leaks data all over the place. Some of them are based on hashes and SHA-1s and MD5s and certain inputs. Some are based on timestamps. Some are based on MAC addresses, all over the place. You can use Burp Suite to automatically identify UIDs in the response. There's a plugin for it. Most Office documents have UIDs baked in them all over the place. Windows registries, binaries, and database record IDs all have UIDs. For fun, I went and dumped all the UIDs out of the Windows registry in Windows 11, ran them all through a script to scrape out the MAC addresses, look at the MAC addresses based on the vendor, and then plot the most common ones. So what were the Microsoft developers running hardware-wise when they allocated these IDs? Well, Intel NICs and Dell NICs were the most common for sure. For all the Windows COM IDs, the MAC address is the most common. The one that threw me though was like 3Com. So 3Com doesn't make computers, at least not recently. I mean, they did the Huawei thing for a while. It wasn't until last night a friend of mine reminded me, hey, you know what? 3C905s, like 3Com, you used to not associate your Ethernet card with your computer manufacturer. You associate it with the network card you bought. Network cards used to be hot stuff like GPUs. You got the latest 3C905 and you're kicking butt with your 100 megabits. So 3Com is actually one of the early network card manufacturers that everyone used, and therefore a lot of the Microsoft engineers who created these IDs in Windows were using 3Com cards at the time, which is kind of fun. And then the DEC one here is because some of the DCRC COM IDs were actually originally registered by DEC. And of course Toshiba, which doesn't really make laptops anymore. So what you're going to see going forward is a lot of your developers are going to say, we're now going to use UID v7 because it's better for database sharding. Unfortunately, you lose about half your random bits when you do that. So it's much better for your database, much better for your S3 prefixes, and really bad for security in some ways. Usually the argument is you probably still have enough of these white bits, random bits left, but you're probably going to see a lot more UID v7s in your application just because there are some good locality improvements. MAC addresses are really fun. It's 48 bits. You can see the Ethernet, Wi-Fi, Bluetooth. They're not just 3-byte prefixes. They're also these medium and small ones, which have different kind of nibble blocks. So it's not just 3 bytes and whatever. It could be 3.5 bytes, 4.5 bytes to get the same thing. So if you want to go identify what something is based on the MAC address, it's kind of, you can go look at the OUI database. But if you want to know the history of that, you have to go find somebody who's done scraping for 20 years to put it together. But yeah, I did that. So you can go to Mac Ages, github.com, HTML Mac Ages, and you can get the CSV file that's updated every day of the allocation history of every Mac range going back 20 years. So it's pulled out of the Wireshark, Manu file, CSVs, and then daily scraping since then. So we can see in this case that Huawei just registered a new prefix on October 23rd. It starts off with 3024B. And this also sets the floor for the manufacturing date. If I now see a Huawei device with this MAC prefix, I know it must have been manufactured after this date. So I have a general idea of how old that device is, which tells me lots of cool things about how old it is. So the thing I'm probably not going to have time to go to today is I scanned the whole internet for MAC addresses and found like 50 million Macs through a bunch of different protocols, and I was doing a big fun analysis of all of them. But one thing that stuck out early on is I saw this weird probe on like port 987, 9302 that it just didn't make much sense. It was a search star HB11. Anyone know offhand what this protocol is? Well, it's a little bit better well known now, but this is the PlayStation 4 and PlayStation 5 discovery protocol. And I only found it out because I didn't know what it was. So I just turned around and took the same pack that I got on my honeypot and scanned the whole internet with it again and say, well, what came back? So that's actually a really fun technique to use your honeypots offensively to steal other people's research before they publish it. You look for them scanning for things, and you say, great, let me just turn around and bounce it across the whole internet and see what you're looking for too. And hopefully it wasn't a shellcode or a payload. So one thing I've been playing in the background is basically scanning all the PS4s continuously for the last 5 days and getting a list of all the things they're running. So you get like the version of it, you get like their status, whether it's in a mode or not. But you also get this ID number. It's PS Disco ID. The PS Disco ID actually kind of looks like a MAC address. It is a MAC address. So you actually get the MAC address remotely for every PS4 and PS5. And these things are exposed to the internet because they auto-UPnP themselves to the internet. So they're actually backdooring your network automatically as part of UPnP. So in this case, we can see that this PS4 was manufactured in 2021. We start looking at all the different stats, the most common applications running on it. You can get a sense for who's playing Red Dead Redemption, Overwatch, YouTube, all that fun stuff. So I've been keeping track of all the most popular games and applications on PlayStations in different countries for a while now. I'll publish that eventually, but you can also see kind of the long tail here of firmware. But I know I'm out of time here, and I'll put the next in line. Short identifiers are everywhere and dangerous, but unfortunately people like them because they memorize them. Long identifiers are better, but they provide really unique, precise tracking, and there's fun data everywhere, so keep your eyes peeled. Thank you very much.